So next, let's look at theorem 4 on page 163, where we have f of x is non-decreasing, okay, pointing up, and alpha of x is continuous. Now you notice now that this situation, if you compare it to theorem 3 of the previous page, you notice in theorem 3, the condition is that f is continuous and alpha is increasing, right? And it doesn't matter, just bear in mind that there's a switch of conditions here. And so, and also this theorem works if f of x is pointing down, okay, as long as it's monotone. But right now, we're just going to focus on pointing up. One situation at a time. Pointing down proves exactly the same way. So anyway, if that is true, then the integral of the Stieltjes integral of f d alpha from a to b is the same as f of a times the integral from a to some point of psi in between a and b. It could be the end points though. So plus f of b times the rest of the integral, okay? Integrating all the way to b from the middle, from the point psi. Again, psi could be the either end point, so bear in mind of that. Now, so next, so let's see how this is proved. The proof is based on theorem 2 and theorem 3. So let's look at theorem 2. What does it say? Theorem 2 on page 160, yes, it says that if f is going up and alpha is continuous, then we have this particular situation. Oh yeah, integration by parts, right? The f is equal to that minus that and then minus this, okay, the original f. And so that is theorem 2. And so bear that in mind for the next 5 minutes or so. Next, theorem 3, which is just in the previous page, right? It says that if f is continuous and alpha is increasing, that's different from what we have right now, okay? The opposite switched. So bear that in mind. But if that is true, we can yank f out of there. Now f is the continuous one. In other words, whichever one is continuous can be pulled out of the integral with some value of psi. Okay, so that is theorem 3. So then, okay, so with those two things fresh in mind, let's look at this thing. What does it say? So first, we are going to apply the integration by parts. So integration by parts says that this thing equals to fb alpha b minus fa alpha a, as we just seen, and then minus then alpha df, right? And then now we're going to yank alpha out of there. A equals alpha psi by theorem 3. Why? Because alpha is the continuous one. And as we said in theorem 3, whichever one is continuous can be yanked out of the integral. So we yank alpha out, okay? And then so we got this equation right here. And this is it. This is what we're trying to prove, okay? And to see that, I have it written. Please write this out yourself, okay? And I have it written out right here. So towards the bottom here, let's see. We have, okay, so that's the equation with alpha yanked out, right? And then we're doing df of x. Now by condition 1, the df of, if you're integrating some constant, especially if the constant 1, that is just the integral is simply fb minus fa. Okay, that is what condition 1 on page 155 says. So this is the integral is fb minus fa. So I wrote down all the other stuff, and then we do some basic algebra. Round up the terms fa and fa here, okay, which we end up with alpha psi minus alpha a. And round up the terms fb here, and then that end up being fb times alpha b minus alpha psi. Now, again, by condition 1, alpha psi minus alpha a is the same as the integral of 1 from a to psi or something like that. Anyway, this equation is identical to equation 5 because we're just shifting the subtraction back into the integral. So then we will immediately get this thing back. What was that? That's what we were trying to prove, okay? So the subtractions go back, and then we got this thing nicely proven, and that's theorem 4. So next, let's look at corollary 4.1. 4.1 says we have a g that's in C, and F is increasing. So corollary 4.1 is comes from theorem 4, with the only difference is that alpha is now G. Okay, so if alpha is G, what we're going to do is do the same thing we did in the previous corollary 3 in the previous page down here, where we have, we define alpha x as this integral right here. In other words, then we apply the fundamental theorem of calculus, then immediately, then the integral of gx dx is the same as the integral of d alpha. And let's see. Yeah. Anyway, as the book says, equations 1 and 3 are equivalent. Okay, so where's equation 1? Right up there. Okay, so take a look at equation 1. See, 1 and 3 are exactly the same. And in the sense that the d alpha is the same as gx dx. And once that's true, then we just plug it in here, okay? If d alpha is x is the same as gx dx, you plug it in somewhere in the theorem right here, okay? Then plug d alpha in, and then everything's identical to theorem 4. So that's how corollary 4.1 is proven. And so, and in fact, corollary 4.1 has a big long name, okay? And but yeah, memorize that name if you feel like it. Otherwise, we'll just move on. Corollary 4.2, and anyway, so corollary 4.2, we have gx is continuous, okay, and then f of x is increasing. That's the same as corollary 4.1, but there's a third condition. That is, f of x, the increasing function, has to be also positive. Okay, it's bigger than or equal to 0. Okay, so it's increasing or non-decreasing, and it's bigger than or equal to 0. So it's on top of the x-axis, or at most sit on the x-axis and be 0. But it's not going to go. F cannot go below, right? Well. Yeah, so if, now that is a fairly stringent condition, right? I mean, how do you know f has to be both bigger than 0 and increasing? But under those conditions, then we have, what are we trying to prove here? Equation 7. Then the integral of fx gx will be equal to f of b times some kind of a psi that could be a or b, okay, or in between, of g of x. So then we can yank f out, okay? And the rest of the integral will start from some point inside the original interval of original limit of integration. Now to prove that, we use one trick, okay? We redefine f of x so that f of a is 0. If f of a is 0, that changes. That doesn't change much, right? Because f of x is still increasing, okay, and fx is still bigger than or equal to 0. So the original conditions of f still applies. We never ask f to be continuous, so the fact that we change f of a just 1 point as dropped it to 0 doesn't hurt anything. So then, as the book says, f of x remains non-decreasing and non-negative, okay? Which means equation 6 is still valid. That is, we can apply corollaries 4.1, where we can get equation 6 right here, right? So this still works, all right? Equation 6 is still valid. But the first term on the right, but however, remember, we just said that fa is 0. So this gets knocked out. So this disappears, and we only get this. And which is why this is happening, see? Because we said f of a is 0. So suddenly something got killed. This term got killed, and then we only have this thing left standing. So that equation holds. Now, however, you have to take care of some point is, well, if we change fa go to 0, does that change the original integration? like over here. Does this change anything if f of a, instead of whatever it used to be, now is forced to be 0? But being that we're only changing 1 point, integration doesn't care about 1 point, okay? Because integration is, this is the Riemann integration, the old-fashioned one, okay? As we have learned before, 1 point does not, integration is the area under the curve, and changing 1 point doesn't change the area at all. So, so the integration value is unaltered, as it says, by changing the definition of f of x, and that's why corollary 4.2 works. Now that's a bit of a neat trick, right? So, but in any case, I should mention that this corollary has the condition of f, excuse me, f is increasing, non-decreasing, and f is positive. But those are not the only possible combinations. We can also have f increasing and f is less than 0, okay? And then, or f decreasing and f is less than 0, and so on. There are, I think, a total of 4 possible combinations, which we will investigate in detail in problem 5 of your homework. So, so we'll do that then. Next. So next, let's look at example A. Now, but before we do that, I want to refresh your memory of what I mentioned earlier in this section, that the Cauchy's criterion for convergence, which basically says if you give is a delta epsilon definition, although there's no delta here because it's a bigger than 1. So basically, given epsilon bigger than 0, there exists a big R, okay, such that for all R and for all R's that's bigger than the R0, then the integral of this thing will be less than epsilon. That is the tail end of the integral will go to 0. And if that's the case, well, I should mention, what are we talking about here? We're talking about then the integral converges, okay? Because we're talking about the integral where the limit is infinity. So so anyway, bear that in mind, okay? That's the Cauchy's criterion for convergence. And now that I've said that, then we can look at example A. Example A says, let's see what it says. On page, first let me find it. We're still on page 163. Okay, example A towards the bottom of the page says that the integral 0 to infinity fx gx converges, okay, so that's where the Cauchy's theorem, whatever it was, comes in handy, converges if f is decreasing or non-increasing, points down, and tends to 0, if f itself tends to 0, okay, as x goes to infinity, and there exists a constant m such that the integral from 0 to r, big R, of g of x dx is less than m for any big R. So it doesn't matter how far you integrate this thing, it will always be less than m. You notice that it doesn't say that g has to be positive or anything, or negative or whatever, okay? G can be whatever, g doesn't even need to tend to 0, as long as g is limited. For example, g can be sine of x, and it doesn't go anywhere, but the integral of sine of x will always be limited because of its cyclical nature. So then, and also we assume that f and g are both continuous from 0 to infinity, positive infinity. Okay, so that's that. So let's now look at the next page, page 164. And see the proof of example A. So first it mentions the Cauchy's something criterion, right? It says, let epsilon be an arbitrary positive number. It will be sufficient to show the existence of a number R0 such that for all numbers that's greater than R0, such as R prime up the R double prime, then the integral of f of x, g of x dx is the absolute value is less than epsilon. That is exactly the Cauchy's criterion, which we will learn later, okay? But right now we're going to pull that out and talk about it, which is fine. And so that's that. It makes sense though, because we're trying to prove this thing converges, and to prove something converges, we just have to prove that the tail end of the sum is going to 0, and no, actually what we're proving is the tail end of any two items, the difference between any two items in the sequence is going to 0. Okay, so the things are getting the entire tail end of the sequence is getting closer and closer to each other. So they got nowhere to be except converge. Well, anyway, we're not going to talk too much about that. As I said, we will learn that in detail in chapter 8, right? So, but in the meantime, we're going to use that thing. So with that, with the understanding of all that stuff, then we're going to use our mean value theorem, of course, that we learned in all this stuff. Okay, so I have it written down. I have a bunch pile of mess here, but doesn't matter. Okay, let's look at the first line that makes any sense. So by equation 6, we'll look at that in a moment. Then we can write this thing that we're looking for. That's what we're shooting for, right? So from R prime to R double prime FGX, we need to work with this and make it do this, and limit it. So by the mean value theorem, equation 6, it equals to the first one, FA, and then the integral, and then FB, and then the integral. And the equations, so let's go back to look at equation 6. Where is it? Which is on the previous page. Equation 6, all right. So that is, here's equation 6. Let's see, okay. We have the integral is of two products, okay, that's similar to what we have here. And then it equals to the first endpoint times the integral to some point inside psi, and then the second endpoint times the integral for the rest of the endpoint to the final point. All right, so that's equation 6, which we apply here. To double check, to apply equation 6, we need g of x be continuous. We got that, they're both continuous. And then we need f to be increasing. Or decreasing, okay? This one works whether f is increasing or decreasing. In this case, f is decreasing, so it works, all right? So then we will then go ahead and apply equation 6. It's very important when you apply any theorem to make sure that all the criterion are met, okay? Otherwise, you can't use it. So now that we have made sure of that, so we write this down. So that by equation 6, it equals to R prime is the A, right? Times from A to psi, and then f of R double prime, that's B, and then from psi to B. All right. Now we are going to make an interesting argument. Since f of x approaches 0 as x approaches infinity, that's one of the given points, okay, we are going to let this term, we'll let R double prime go to infinity, okay? And in other words, this term is as small as we want, so we'll just figure it's 0 and ignore it. So this whole thing is ignored. This whole thing has become 0, and then it's a goner, okay? So the only thing we have to think about is this. So this equation equals to that equation. Now that is what the book says. That because R can be as big as possible, right? Let's see. And what the book says is that right here, okay? Under the present hypothesis, the second term on the right of 6 may be made to disappear. Okay, remember that's a better way of saying what I said. Okay, let's pretend this thing doesn't exist, because R can be as big as possible. So let's make it really, really big, and then it's an extremely small number that we'll ignore it. Got it? which is quite a funny argument. Okay, so continuing, we have only one thing left. Okay, so then the one thing is what we're going to pull out the next mean value theorem. We're going to yank right here. All right, now this, so the next step right here, we have this thing which we're going to yank, which we already established. We already did the yanking. It equals to that, okay, with that thing made disappear, as the book puts it. So the absolute value is going to be less than or equal to this side of this thing. and which right now it's only equal, but we'll make it less than equal to real soon. But anyway, so equals to that, all right? And what is that? The one that I have underlined pink. This integral, just the integral, okay? Yeah. Maybe I shouldn't have underlined this part. So just the integral is the same as that one, right? Which each integral is less than m. Okay, each one of these integrals are less than m. So the two of them together is going to be less than 2m. So that's where we got the 2m out of. As f, now this is less than epsilon, because as f goes to 0, as x goes to infinity, or r prime goes to infinity. So then this whole thing can be made to be less than epsilon as long as you pick r prime big enough. So then we are going to choose the original r0 that we require to be something smaller than r prime, and then we're good. Okay, then the entire proof is finished. Now this proof is slightly twisted, so it might take a little time to get used to it. See, that's why I have a look at all the stuff I keep trying to say and then change my mind and didn't think that was a good way to explain it. But if you just read it very, very carefully, okay, one step at a time, and make sure that you understand each step, and everything will come out and to make sense. So, okay, and especially the part where we make this thing disappear, okay, that is slightly tricky, but if you think about it long enough, it will make sense to you. So that is example A. And with that is the end of this section, and we should do some homework. For homework, let me find it. So for homework on page 164, please do problems, let's see, okay, 1, 5, 6, 10, 11, 12, 13, 14, 15, 16. All right, and when you're done, I want to talk about them. So let's first talk about problem 1. We have, let's see, that one you just let in the corollary 3, you let g equal to 1, okay, then plug it in and everything will show up nicely in one line, basically. All right, so that's that. And next, let's consider problem 5, which is considering all possible combinations in corollary something. What is that? Corollary, let's see, 2. Right. So it says we should consider 2 other conditions. So I list all 4 conditions. The first one is the one the book proved, okay? And then there are 3 other possibilities, because either f is going up, f bigger than 0, f go up, f less than 0. Now, if f goes up and f is less than 0, then what we're going, instead of setting fa equal to 0, we set fb equal to 0. But otherwise, the whole thing looks identical, okay? Because then the integral will end up being fa times something, being that fb is 0. So that is how that will come out. Similarly, the third, for the f going down, third and fourth situation, the story is very similar, as you can see here. So please write all that out, and then that's good. So then next, let's look at problem 6. Problem 6 is interesting because we are supposed to now assume corollary 4.2 is true. That is, we're all done with corollary 4.2, and now we need to prove corollary 4.1. Now, how interesting, because originally, I think corollary 4.1, yeah, 4.2, I think depends on 4.1. Yeah, it does. That means the 2 corollaries are equivalent, okay? If both things come together, you know, A implies B and B implies A, then they are in the both sides pointing, that is the if and only if situation. Anyway, so we assume corollary 4.2, and then we're going to prove corollary 4.1, and 4.2 gives the condition that G is continuous, right? And then F is up arrow, and then F is bigger than or equal to 0. And then, well, anyway, so continuing, then the integral, you can yank FB out, right? That's the first one that we proved. Now, we have to prove corollary 4.1 with this, but in that case, we no longer, let's see, but we don't have the f bigger than 0 in there. All right, so that is that condition is no longer available, but we still have to show it. Okay, so to do that, we're going to create a function that is bigger than 0. We'll just let h equal to f of x minus f of a, and since f is an increasing function, then h of x has to be is bigger than or equal to 0. That's because f is, we know that f is bigger than 0. So it starts out bigger than 0. fa has to be bigger than 0. So then h of x is bigger than 0, at least for the interval ab that we're talking about. Now, knowing that, we're going to apply corollary 4.2, the given one, to h. Okay, so we write it in h, which by the corollary, it means that this integral equals to h of b times some stuff. Okay, and then we're going to plug in the h of x back. Okay, that is now back into this, that is replace h of x with f of x minus f of a, its own definition. I'm going to do the replacement immediately. So then we get this equation right here. Okay, this is h of x, right? This is h of b. H of b is fb minus fa, and then we write this thing out. Then we get this pile of stuff, and we realize that this is, when we rearrange terms, we realize that the fa terms, this is, when move this to the other side of the equation, we get f of a, we can pull it out, right? Why do I have it written inside? Doesn't matter. It's because of this. All right, so then we can pull the f of a out of the integral, and then becomes that end up, this thing put on the other side becomes positive, and then subtracted by that, which is the same thing, except for the limits. So we end up we are doing from a to b minus psi to b. So we end up with a to psi, and otherwise everything would look exactly like corollary 1 that we are trying to prove. Okay, this is a psi here. Anyway, yeah, so everything checks out if you look at it carefully. Let me, why is this not, whatever, it's good enough. Next, let's look at problem 10. We're going to prove some sine x over x going infinity converges, okay? That is using our current rules. Then we have, and that works quite fast, right? If you let f of x is 1 over x, g of x equal to sine of x in example A, and which satisfy all the conditions, and then therefore it converges. So that's about it. Problem 11, the same, okay? And because x minus p to the power minus p is a decreasing function, positive, all that stuff, and it goes to 0, therefore something converges. What converges? Doesn't matter. It's the same as example 10. So next, let's look at example 12, which states that the integral fg converges. That's again example A. The integral in example A converges if f and g are continuous, f is decreasing and bigger than 0, and the integral of g converges. Okay, so that is a lot of nice, comfortable conditions, which were well provided for. Okay, so then so we'll do something similar, simulate example A's proof, where we have we'll consider this integral right now. Okay, and then apply the MVT. I don't know which corollary this is, but anyway, it equals to the first endpoint and then the second endpoint added together, which is being the f is a decreasing function, we'll just say that factor out the first endpoint multiplied by both integrals, okay? And both integrals are going to 0 as r goes to infinity, and therefore the whole thing converges. Yeah, that's good enough for me. So that's next, let's look at problem 13. We're going to illustrate problem 12 by an example where f infinity is not 0. Okay, that is, here's my example. We have problem 13. I let f of x is identically 1, then f infinity is not 0, and f is pointing down. Well, at least it's non-increasing, right? So then it satisfies all the conditions of whatever. And then I said g of x equal to x plus 1 to the power minus 2. Then the integral is readily calculated, which is, whatever. So that is problem 13. Next, let's look at problem 14. So problem 14 says, under the condition of theorem 3. So let's look at theorem 3. Theorem 3 says if f is continuous, alpha is pointing up, then the integral equals to, you can yank the f out. Okay, that is theorem 3. So bear with that in mind. We are now, problem 14 says that, all right, so we have if f is continuous, alpha going up, find that limit of that thing. All right, so the limit of that thing is equal to, by theorem 3, we can yank the f out, okay? F is continuous, so whichever runs continuous can be yanked out. So we yank the f out, and then of the limit, okay, so it's still inside the limit, then we break it up into two limits, because you can do that. The limit of product is product of limit or something like that. So if we break it into two limits, both with, one is, so then in the second limit, does f psi, then psi has to go to a plus. Right, and so as a result, then the f being continuous, that's just f of a. So the second part stays, and that's another way of saying this is this limit just becomes alpha a plus, which is the same as saying that limit. Okay, and that is the right answer, and that is problem 14. So next. So problem 15, we'll go ahead to use the idea of problem 14 and property 5. Okay, this is property 5 on down here, property 5, where it says that if you have alpha is broken up into alpha 1, alpha 2, then we can break the whole integral into two chunks of alpha 1 or alpha 2. Okay, so with that in mind, we are going to do problem 15, where so problem 15 has some weird two weird things happening. So we'll break it into two pieces, right? And then one of them is continuous, so that's just going to be 0. So because we're forcing x to go down to 1. And so that's just 0. What about the second thing? The second thing will follow problem 14, which says it equals to this. Okay, and this is end up being equal. That depends on what the bracket t is. Well, bracket t from 0 to from 1 to what are we integrating? Give me a second here. I might have this might not be right. Let me check. Actually, I'm okay. Now, bracket of t where from 1 to x is just 1. Right? Because the bracket is whatever integer is less than or equal to the number. So starting at 1, 1.1 is just 1. Bracket of t is just 1 for and next to near 1. So so as a result, this is a constant function, which means the change. Where's my d here? I'm missing a d. No, I'm not missing a d. I thought that looked something else. Anyway, so dt, that is just, that's going to be 0 times e to the, and then we don't even care what e is. E is just 1 at that point. So that's so the whole thing add up to be 0, and that checks out with the back of the answer as well. Next, let's look at problem 16. Now, problem 16 is to prove that statement we made at the end of proof corollary 4.2, where we said that if two functions are the same except for 1 point, then their integrals over the same interval are the same. Now we're going to actually prove it. Okay, that is, we have a function, right? It's continuous, and then there's a different function that's exactly the same function except at 1 point. The initial point. Let's just show that the integral of these two things are the same. All right, so so here's what I came up with. There's probably more than one way to skin this cat, being that the cat is obvious. Okay, but here's what I come up with is let's see. So let's say f equals to so f is c. Okay, let's see, this part is bulging out. Move it down a little bit. Okay, that should be good. So f is continuous, and g and f are exactly the same except at one point. We need to show the integrals are the same. So I pull out another function called p of x, okay, being their difference, which means p is equal to h at a, right? And the rest of the p is equal to 0. And then let's assume h is bigger than 0. And that make it easier to talk about. So then let's say the integral of p of x from a to b is equal to a, and we need to show that a equal to 0 because that will make the two the same. Now to show a equal to 0, I am going to let w, which is the width, equals to a divided by h, like this picture shows here. There's a, okay, and h, and a divided by h is going to be w. Now, this is possible if h is not well, never mind h. H is not 0. That's fine. Let's see okay. And then we define another function q of x, being h from 0 to from a to a plus w's. That is, in this range, the q function is going to be h, and it is going to be 0 otherwise. All right. So as a result, then p of x is only h at one point, whereas q of x is h at a potential range of w. So p of x is less than and equal to q of x, and so a, which is, as we defined before, is the integral of p of x, right? Which is the same as the integral from a to a plus w over 2. So we're only integrating to a little bit. But that makes no difference because p is 0 except at a. So that will be fine. Okay, so that is the less than equal to q of x integrating to the same area. Now q of x integrating only half that much, w over 2, is going to be equal to a over 2. Right? And so as a result of that, which means a equals to a over 2. The only way that's possible is if a is 0, and that's how we have proved that these two integrals are the same. It's kind of a weird little proof, but proving what's obvious is hard, okay? And that's the best I can come up with. So that marks the end of this section.